with the learning objective we have here, we're going to apply cryptographic algorithms to messages. To do that, we need to have some background, which for cryptographic algorithms is mostly going to be modular arithmetic. And we're also going to use a little bit of probability. So cryptography is the study of secure communication. And security is a broad field. It can refer to a lot of goals, but typically we're going to care about confidentiality of information, authenticity of the information, and integrity of the information. And in particular today, we're going to be talking about confidentiality, which means that we are going to be talking about encryption schemes. So taking a look at this diagram we have here, in encryption schemes, we are sending messages securely in the presence of eavesdroppers. So here I have Alice, a sender, and you can see that because the arrow points to the right, and then Bob is going to receive the message, so he is the receiver. And so Alice has a message, she has a key, and she's going to encrypt it to create a ciphertext. That ciphertext is going to be sent along this channel. Bob is going to receive that ciphertext. He also has that same key, and he's going to be able to decrypt it to find out what that original message is. Now, Alice and Bob's channel is insecure. An eavesdropper can see the ciphertext. They just shouldn't be able to figure out anything about the message just by looking at that ciphertext. In other words, we want only the people who can decode the message to be the ones who know the secret key. So confidentiality basically means that the adversary here in the center cannot figure out the message just by looking at the ciphertext. And so taking a look again at this channel, I have C, and there's this person in the middle called an adversary, whom we often refer to as Eve because they're an eavesdropper. So we have Alice, Bob, and Eve. And even if that eavesdropper sees that ciphertext, they still shouldn't be able to figure out anything. An adversary is a malicious party who intercepts the ciphertext over a channel. The adversary knows everything about an encryption scheme, like how the encryption is done, how the decryption is done. The only thing that they don't know at the time is what that secret key and the message are. So let's go ahead and look at an example of an encryption scheme. And so here, this is a shift cipher. So thinking about that, we are shifting our letters by some amount. This is also known as Caesar cipher, so it's, a couple thousand years old. If you have the letters and you write them through and say A is 0, B is 1, going up to Z is to 25, then you can think about shifting the letters by some amount individually. So here I have K is equal to 3, and I'm going to say we're going to shift each letter to the right by 3. And so thinking about that, we're going to have A is 0, and then D is 3, so adding 3 is going to make A go to D. And so one thing here is to remember that once we get to Z, it has to somehow come back to A, and I can't exactly add 3. But if I think about it in terms of modding, then everything works out. So here I would say that I have my encryption, which is going to take that letter, let's call it I, and then let's add whatever that key is, and we're going to mod it by 25. Right? And so that's going to give me my ciphertext. And I'll call that CI. Meanwhile, for decryption, I'm going to have ciphertext CI, I'm going to subtract K, and I'm going to mod it by 25, which is going to get me back the original thing. And a couple of things more to point out here. We're really modding by N in general. It's just that here N is 25 because that's the size of the alphabet in English. And these messages, I've done MI. It's a single letter because we're going letter by letter. And so thinking about a message would be M1, M2, all the way up to however long your message is, let's say L characters long, and we're encrypting each of these to be a ciphered version of that message. So just to remember, just to go over it again, the key is going to be +3 because I'm going to go to the right by 3. And then when I go to decrypt, I'm going to shift left. So it's kind of like subtracting 3. So here's my key. And in general, it's going to be K. And we can see that K is going to be from our key space, which is going to be a number between 0 and 25. So let's go ahead and let's try an example. I have the shift code and I want to decrypt the code, assuming I'm just going to have only capital letters. And I wanted to point out here that there are websites. There's this one website called decode.fr, and you can look up the Caesar cipher here to actually run a brute force on this. So let's go ahead and take a look at it. And so here we have my ciphertext. And the ciphertext that I had in the example was QEXL MW JYR. We can decrypt it. And as you go through, you can see if I shift everything over by 4, +4, I'm going to get math is fun. Now I could shift it by all these other kinds of values like 17, and I would get ZNGU VF SHA, which doesn't really mean anything. And so the key for the encryption is +4. And so we shift everything to the left by 4 if we want to decrypt. So going back to the example, we've concluded that the encryption, this is the encryption of math is fun, and that my key is +4. So you can definitely brute force it just by running through all the possible keys that I have. Let's talk about the formal definition of an encryption scheme. It is composed of 3 polynomial time functions. So I've written here that it's O of n to the c. So c is a constant, and I have n as the input size. And we have these 3 functions, which are keygen, encrypt, and decrypt. And so since I have these 3 functions, I often write it as a tuple. So you might say an encryption scheme is a tuple of 3 functions, keygen, encryption, and decryption. The first function I have is keygen of n, and that's going to give me my key k. So k is going to be my key. N is what's known as a security parameter. And the security parameter tells us how long our key is going to be. That basically defines how much randomness we have, or how strong our encryption scheme is. So for example, with RSA, which we'll talk about in a bit, you might have 4096 bits. That's how long your key is, and that indicates how secure that encryption scheme is. 4096 would be considered more secure than, for example, 128 bits of that same type of encryption scheme. Next, I have the encryption function, which is encrypt of m and k, and that's going to give me c. So again, k is my key, m is my message, also known as the plaintext, and c is what's known as my ciphertext. The ciphertext should look random. To anyone that doesn't have the secret key. Last, I have decryption, so decrypt of C and K, and that's going to give me back M, my message. So decryption is used to reveal the message inside the ciphertext. So again, I have C ciphertext, and C gets decrypted to reveal the plain text M. And going back to thinking about Bob and Alice, so I said that they had an insecure channel between the two of them, but earlier they must have somehow shared a key. So the way I often think about it is that there was a secure channel. Maybe Alice and Bob met in a coffee shop ahead of time, or had set up some sort of secure way to talk on the internet, and so they securely shared this secret key to each other. And it's only sometime later, when they're far apart, they're no longer in the same coffee shop together, and Alice wants to send that message to Bob, that she has to use this insecure channel, but luckily they both already know this key K. To formalize a little bit more some of the things that we care about in terms of cryptography is we need to think about sets. So as usual, we're using capital letters to reference these sets. And so I have here the capital letter K, which is going to represent my key space. The key space is a set of all possible keys that we could use to encrypt our message and later decrypt the ciphertext. A couple of examples here. So K could be the binary strings of length 3. In this case, I have 8 possible secret keys. So binary strings is a typical sort of key, but 3 is very short. We would normally have K being 0, 1 to the 128, or I think I also mentioned 4096, so it's quite a bit larger than just having 3. Another kind of example that you could have for keys is to say, think about it in terms of integers. And so the more numbers you have, if I just say it's these positive integers, and so for Caesar cipher, I said it was maybe the integer 0 to 25, but I could go to really a large number. Something like that. That's another possible set of keys that I could have. Next, I have the message space. So again, I have that positive, I could have M be that positive set of integers, some subset. We could do a mod. We can also do strings from letters from the English alphabet. And typically, we're going to use the capital letter M to denote that message space. Lastly, I have the ciphertext space. For now, we're just going to say that the ciphertext space is going to be the same as the message space. Now that I defined this notation, the nice thing about that is I now have this definition of what it formally means for an encryption scheme to be correct. An encryption scheme is correct if for all M and for all K and K, the decryption of the encryption of M and K with K is going to give me back the original M. So in other words, for all M in M, for all K in K, decrypt of encrypt of MK, which is going to give me some ciphertext, with that same key is going to give me back the original message. Let's understand these definitions a little bit better by going back to the Caesar cipher and formally defining it. So in this case, I have keygen of n, and I said, in this case, we could say n is, actually it's 26 because it's going to be the numbers 0 to 25. And so that's the space that I can select from. And so thinking about that counting, this is going to be the size of whatever alphabet I want to use. And we are, of course, also going to be using modular arithmetic. to be able to do the algorithms here. Next, I have the encryption, and we shift each letter of M forward by K mod 26. And so the way that I've thought about that is M is a string, which is composed of characters. So I have M1, M2, up to ML, and then the encryption is really M1 plus K mod 26, and then the next letter is M2 plus K mod 26 up until we get to that last letter. So for example, let's say I had M and I want to have cat. And I'm going to say K is equal to 2. Then shifting everything forward by 2 letters, thinking about A, B, C, D. I know A is 0, B is 1, C is 2, D is 3. And so C plus is 2 plus 2 mod 26 is equivalent to 4. And 4 is going to be E. So the encryption for this one, cat with K is equal to 2, is going to be E, C, V, going letter by letter. And because of the modular arithmetic, remember that we're going to wrap around. So for example, if my message were literally just the letter Z and we had a K of 2, then going back around, Z is going to be 25. 25 plus 2 is 27. Mod 26 is going to be 1 mod 26, which means that it's going to be equivalent to the letter B. So in this case, the ciphertext would just be the letter B. Next, we have the ciphertext, and we want to be able to decrypt that, and we're going to shift each letter backwards by K. So thinking about that ciphertext in terms of C1, C2, all the way up to however long it is, the ciphertext is going to decrypt as C1 minus K mod 26, concatenated with C2 minus K mod 26 for each letter. So looking at an example here, let's say that my ciphertext is FQI, and I have that K is equal to 2. Then we can say, let's just shift everything over. So F is actually 5, and I'm going to do 5 minus 2 mod 26, and that is, of course, 3 mod 26. That's going to be D. And if I do that for each letter, I'm going to find out that this original message is going to be dog. And so now that we have that Caesar cipher formally defined, we can actually prove the correctness. So remember that with proving the correctness, what we want to show is that for all M in M, for all K in K, that decrypt of encrypt of M and K with K is going to give me back the original M. So let's say proof, and we say let M be an arbitrary string, where I'm going to set M is equal to M1 up until ML, because it's composed of letters. MI is some letter or some character in M. Because the Caesar cipher shifts letter by letter sufficient to show correctness for one letter. Okay. So a couple of things to point out here. When you're writing your proofs, using this word arbitrary, saying that we selected one because I had a for all here, so I just want to pick an arbitrary string. And then the other thing is saying that something is sufficient to show. So moving on from there, let's go ahead and think about the encryption of MI with K. Well, before we do that, we need to say K is an arbitrary key of K, capital K, the set K. All right, and so now finally, let's go through with the equation. And I start out with just plugging in the definition and then saying what that encryption is. So we know that for a single letter, encryption is MI plus K mod N, where N is the length of the alphabet. And now, going through with that, we need to decrypt it. So the decryption is going to take this, MI plus K mod N, and I'm going to do minus K mod N. So now, thanks to the rules of modular arithmetic, we can rewrite this as MI plus K minus K mod N. And we can conclude that K and K cancel out, so this ends up being equivalent to MI mod N, which is the original message. And so since we picked an arbitrary M and an arbitrary K, then we conclude that it's true for MI, and therefore it is true for all I in 1 through L, which is the length of my string. We can say decrypt of encrypt of MI, K is equal to MI, conclude that M, which is equal to MI through ML, has decrypt of encrypt M, K is equal to M. And that's it. That's our proof.